Welcome to Earth Science, everybody. It's time for the Bead Drop Lab, which is like a classic Earth Science lab. And another one that I wish you could just be here for and do, but we're almost to the end of this thing. I'm going to go down in about an hour and get my second shot. And hopefully next year we can all have a normal school year. We'll see. For now, a little bit more YouTube. Thanks for sticking with me. I really do appreciate it. And I recognize that it's frustrating / boring. But it's what we're stuck with, yeah? So here's the premise of this lab. To think about mainly deposition, but erosion can play into it too. We're going to think about different size particles. And I've got little baggies of beads here. 12 millimeter, 4 millimeter, and 8 millimeter. 4, 8, 12. We're going to think about how long it takes for them to settle in water. So I've got this big tube of water here. And what I did was, let's pick you up. What I did was I drew like a purple line right here. I don't know how visible it's going to be. Right there. Above that is a little bit of water, which is good. So when I drop a bead in, I'm going to want it to see how it wiggled for a minute and then started sinking at its regular rate. I want that to be a thing. I don't want to drop in and have that strangeness at the top count for the time. So what I'm going to do is drop it in, and then I'm going to start the timer when it hits that line. And then it's going to sink, and stop the timer when it hits that purple line right there. And then there's a space at the bottom for them all to just gather up, and I'll clean it up later. Those two lines, and it is important at some point in this lab, though I don't think I have a place to record it. Those two lines are 50 centimeters apart. It's going to come into play right here when we do the change in value. I'll help you out with that when we get to it. Okay? So they're 50 centimeters apart. And, we're going to do it. Now, there's 15 trials of each size of bead. So I've got to do this, and I'm going to go as fast as I can. But we've got to sit here and drop 45 beads into this tube of water. And, I recognize the absurdity of it all. Drop 45 beads into this tube of water, time each one, write it down, and move on. So that way we'll get a bunch of data. We will get an average of all of those. Then we'll take a class average. I went back to one of the old classes data, and I actually took all 4 groups and averaged all of their trials. And I have those numbers right here. So we'll stick those in there, graph them up, try to figure out the relationship, try to figure out how long it would take different size particles. I don't have a bead that's size 10, but could we figure it out using our graph? Yes, we can. A couple easy questions. This one, by the tedium is going to be the hard part. This is going to be just drill in all these numbers. Once we're done with that, you guys are going to shoot right through this. It's easier than the last couple labs. All right. Let's do it. We've got 4 millimeter beads. 8 millimeter beads, which are blue. The small ones are red, medium ones are blue, and the large ones, which are white, are 12 millimeter beads. All right, these are the fancier beads. They should be a little bit more consistent. I used to get some pretty erratic results on this lab, and I think there's probably still a question. Yeah, this question is going to be about how erratic the results can be, but these beads are a lot nicer, so I think we'll shoot right through it. All right, I'm not going to be writing the numbers either, so you got to listen. And we'll try to do this as fast as possible. I don't know what camera angle's most or least interesting, but what do you say? Here we go. I'm going to go get a taller chair. Okay, here we go. And again, my goal is going to be to go as fast as possible. Oh, my goal is going to be to open up the right app. Here we go. .43. Actually, let's call it 4.4. That was number 1. I'll get faster, folks. 4.6. 4.6. 4.7. 4.7. 4.8. Weird, they're slowing down, huh? 4.3. There goes that. That was number 7. If you're keeping up with us, if you missed it, go back, fix it. 4.2 for number 8. 4.6 for number 9. 4.7 for number 10. 'Missed it, sorry. 4.8. 4.5. 5.0. 4.7. And our last one for red. 4.8. Okay, not bad. So that was all 15. If you missed it, just go back. That didn't take long. You can do it. And reasonably consistent. Again, with the older, cheaper beads, there will be a lot more difference between them. And I'll say, I know it's probably tough for you to watch these things. Maybe the blue ones will show up better on camera. I don't know. But sometimes they get like a little air bubble stuck on them, and that slows them down a little bit. But that's the value of doing a lot of trials. I know this seems tedious, but if you do a lot of trials, you end up weeding out the small errors that might take place. And then if we consider class averages, then we're really, by the time we do that, that was probably 40 groups, each dropping 15 beads of each size. So that's a lot of data to go into those averages, which is good. That gives us like kind of the best results. All right, here we go. 8mm beads, medium beads, blue beads. Let's do it. $3.9 is our first one. 3.9. And now we'll just keep ripping. Uh, 3.0. Not that one. Sorry. 3.2. 3.0. 2.8. 3.3. 3.0. 3.4. 3.5. Now this one will be number 10. If you miss some, go back. 4.1. Ah, missed it. 3.0. 3.4. 3.3. 3.2. 3.1. Excellent. All right, that's all of those. Which brings us to large. Not too bad, right? We're cranking here. We can do this. Yeah. All right, large beads. Same thing. 15 trials. These are 8 millimeter. No, these are 12 millimeter. So starting right up here. Let's do it. 2.8. Our first trial is 2.8, and then we'll just get moving here. 2.8. 2.9. 2.7. Ah, missed it. 2.5. 2.9. 2.7. 2.7. Again, that was minute 8 was 2.7. If you missed some, go back. Oop. 2.7. 3 in a row. Ah. Okay. 2.9 was our 10th bead. Come on. I should be getting better at hitting this button. Not worse. There we go. 2.7. 2.7. 2.5. 2.7. Last bead. 2.6. All right. There's all your data. If you missed some, you're on YouTube. Go back and rewind and figure it out. Let me hit pause here quick, and we'll talk about how to do the graph and wrap this thing up. Not too bad. Okay, so I took the numbers we'll need, figured out this graph so we can do these axes together to save you some stress. Let's do the bottom is easier. The x-axis is easier. Let's do that first. So I'm going to blow this up a little bit here. I recommend this because this graph is kind of small. First off, don't panic. I know there's a lot of numbers there. You're only going to be plotting 6 total points. Don't worry that you're going to have to plot like a million things here and lose your marbles. All right, maybe 300% is too much. 200% we'll have to do. Okay. On bottom, always wise to label your axes if you can. This is going to be particle size. And we did that in millimeters. All right, so what I'm going to do, the origin right here, putting a line down, is going to be 0. And every box is going to be worth a half a millimeter. Now, to save myself some stress, I'm just going to label every other one as 1 millimeter. So there's 1, skip a box. And we're labeling the lines. Okay, so on and so on and so on. And if you do that right, and this is important that you do, I'm going to leave it to you. I'm not going to do the whole thing. You should get to 15 right here. And I know you might say to yourself, well, our beads only went to 12. Why do I need 15? You will, I promise. Okay, so put that all the way there, number all those, you'll be good to go. Okay, over here on the y-axis will be time. This might be kind of hard to squeeze in there. Time, if you hit enter, you go down. And I'm going to make that pretty darn small. There you go. Font 10 seemed to work okay. That gives us enough space. Now it would be nice to go by 0.1, but we just barely run out of room. So we're going to have to go by something slightly different. We're going to go by, this sounds weird, but don't let it scare you. We're going to go by 0.125. So the origin is still 0. And that would mean that every other box is basically a quarter. But again, let's save ourselves some stress in labeling like 100 things. I'm going to make this bigger for the very bottom here so you guys can see it nice and easy. Okay. What I'm going to do is go 4 boxes, so 4 lines really. So 1, 2, 3, 4 to right there. That would have the value 0.5 seconds, half a second. Then another 4 boxes is another 0.5. 1, 2, 3, 4. It was 1 second. Not so bad, huh? 1, 2, 3, 4. 1.5 seconds. And if you want to do the little text boxes for this, it's okay, but make sure you like make the mark there so that you know and we see where you're at. Okay. I'm going to do the rest of those real quick, but I'll pause so you guys don't have to watch that. Be right back. All right. And you guys should pause too to get that all squared away, get that y-axis all set. If you did it right, you got 5 seconds right at the tippy top, which is higher than we need to go, but good. Right where we want to be. Okay. And also finish off your x-axis probably before you go on with the video. So that you are good to go. Maybe I'm going to do one more here so that I can get to showing you how the dots work. Okay. So keep that up all the way across the axis, and you'll be good. All right, so let's talk about your job. Again, don't panic. You do not have to plot 45 points on this. You're plotting 6 points. You can do that. It's not too scary. The first 3 you'll plots, or maybe the second 3 you'll plot, depending on the order you're going to go in, are these 3 right here, your class averages. So pick a color. Maybe you're going to want to do those in blue. You can do this transparency. I like this transparency trick if you haven't noticed. So we will say, hey, I'm going to make those blue, or whatever color you choose, and then make those dots blue, right? And maybe these ones will be red, or again, whatever color you pick. Oh yeah, look at that coloring job. Okay, now that's it. All you got to do is plot those 3 and those 3. 3 dots in blue, 3 dots in red, and you're good to go. Okay, now I don't know what these blue ones are yet. You got to calculate those. So you have to do an average of those 15 trials. That means add up all 15 of those and then divide by 15. And then check your work by looking at it and saying, is that average like pretty close to all those numbers? These are all in a pretty narrow range. So if you see a whole bunch of 4s and you end up with an average of 15, you got to say to yourself, hey, self, I probably hit the wrong buttons on the calculator at some point. I got to start that over. Okay. Our class averages from 2 years ago, a result of about, I'd guess around 40 groups, are 4.5, 3.1, and 2.6. Let's make it red since I'm going to plot in red, right? So there's my 3 points. To plot them, all I'm doing is going by the size and the time, because that's what our graph is comparing, right? The size of the particle and the time it took to settle. So with a red dot, and we'll make it like dot size, like 8. Put my transparency back up here. Will be 4 millimeters was 4.5. So 4 millimeters all the way up to 4.5. Boom. There's a dot. I'll do all 3 class average. Why not? What the heck? Of course, that means I should have not been lazy and written my numbers. Let me be not lazy and write my numbers. But I'll pause. All right, numbers all written. Next points in red for class averages, and these should look the same on everybody's really. 8 millimeters, 3.1 seconds. So at 8 millimeters, right about there. But I didn't miss the line. Don't think I did. At 12, 2.6. Right about there. All right. That's it. Now, I'm going to go slightly different on what we're going to do for our line. I believe that you've heard of these in math, but I guess I shouldn't promise that. We're going to do a best fit line or a line of best fit. Make it the same color as the dots. And do this line tool. I don't want you doing it freehand because then there's probably going to be a bend in it. What's one line would best represent those 3? Now, those 3 are not in a straight line. You can't put all 3 on one path. But what line comes closest to trying to hit all 3 of those? I don't know if you've played with this line tool in Cami or not. I haven't. But let's see. I don't know if we can like manipulate it after we do it. Maybe if you go back to pointer. I mean, I'm pretty much happy with that line. Yeah, but if you go to the pointer tool, then you can adjust it. So if you chuck it on there, you don't love it, go to the pointer tool, which is this thing right here. Then you can grab that line and adjust it. So this is good. Actually, this is where like the Chromebook thing, as frustrating as it is, maybe works out better because you can play with it after. Now that'd be terrible. That would be terrible. What is it's almost like doing an average by eyeballing it. What in your head looks like it is the closest you can come to representing those 3 points? I'm thinking that's about good. Okay. Do please go all the way to the edge of the graph with it. Okay. It looks like here we're saying that smaller ones would take more than 5 seconds. That's okay. We're not going to do smaller ones because the one of the premises, well, one of the first questions you're going to do right here is how quickly would a particle of 10 millimeters settle? And you're going to do this problem twice. It's not really a big problem. Once with your data and once with the class average. Here's how you do it. This is called interpolation. We didn't have a bead. In fact, they don't sell beads. I wish they did. If they sold beads that were this material, that were 10 millimeters, we could run all this, then see if our math worked by then doing a 10 millimeter trial. But we can't. So here's how you would do that. Go to 10, go up to the line. It hits there. Come on over and tell me how long that was. How long would it take? You're predicting how long it would take that particle size to settle. Okay, so do that with the red line for the class average, with the blue line, or again, whatever colors you pick for your data, which I currently don't have on this graph. Do please remember you got to do this twice. Once for the class average, once for your average. Okay, extrapolate is essentially the same concept. There's not really any difference, except that it's outside of our data rather than inside of our data. How quickly would a 15 millimeter particle settle? Well, there's 15 millimeters, up to the graph, over, and tell me how long. Keep in mind, again, every 2 boxes is worth 0.25. So do your best to estimate every 1 box is worth 0.125. If that gets to be too much, as long as you're in the right ballpark, we're not going to panic this year. Okay? These questions, these two always confuse people. But let's think about this as an idea. If we had to compare, let's go a little smaller, rates versus time. Because these sure sound like they're the same question. If you look at them at the beginning, question 3, what's the relationship between particle size and settling rate? Question 4 is what's the relationship between particle size and settling time? They look like the same question, but they're different if you really think about what the word rate means and what the word time means. Okay? So let's say I were to race one of you. In all likelihood, most of you are probably faster than me. Let's pick somebody in class who's a track athlete, right? If I were to race you from one end of this hallway to the other, which one of us would do it in a lower amount of time? That would be you, because you're faster. So this would take less time, so your time is lower. But how did you get there faster? It's because your rate was higher. So see how these two questions ask slightly different things? So if remember we always answer relationship questions the same way. You start with as, and then give me the first variable, which in this question is particle size. You can pick increases or decreases, whatever you want. Let's do increases. Then settling rates. I'm not going to answer it. I want you guys to figure it out. What happens to the settling rates? Speed. What happens to the speed as you get to larger and larger particles? And then this answer is going to sound similar at first as particle size increases, settling time does what? What happens to the amount of time it takes for a larger particle? The answer is different. 3 and 4 do not have the same answer, so be careful there. How does this relate to what we would observe in nature? It's just meant to show that, like, okay, bigger particles settle blank. What do you think? How would moving water affect different sized particles? Well, if a smaller particle takes longer to sink in the water, moving water is going to be able to carry it further down a stream. Sevens is one I mentioned while we were doing it, that like if there's a little bit of variability, which we've decreased by buying more expensive beads, but what things could be off. Sometimes there was an air bubble. Some of them, I don't know if you can see it on camera, but some of them kind of got stuck to the side and like banged along the side as they went down, therefore went slower. So those little differences give us some variability, but again, that's why we did so many trials, to weed out the averages and get us there. don't skip that question. Give me something nice and simple there. You'll be okay. Rate of change problems, which we've gotten to a point where I'm hoping you guys are just like cranking these out. Rate of change, essentially speed, is how much did the value change divided by how much did the time change. So the value is how far that bead traveled, which was 50 centimeters. And then you're going to divide that by how long it took. Well, look at the size of this arrow. That's an arrow. But the top number on each one of them is going to be 50 centimeters divided by how much time it took for basically your 3 averages and the 3 class averages. So those 6 numbers. These 6 problems are all pretty similar. They will all look like this. When we do these, I do want you to tell me what you're doing. Don't just put a number in this as an answer. You're almost there. You've fought through this much of the lab. You guys can do this. So all 6 of them should look like this. In fact, I'll do the one below it because I don't know what this number is yet. You guys got to calculate the average. There you go. That one's set up. This one I can actually do. So yes, I do want to see this. If you just give me the numbers and expect your points, it's not going to happen. So the bead traveled 50 centimeters. According to the class average, the small bead did that in 4.5 seconds. So the average speed is 50 centimeters for every 4.5 seconds. Sorry, taking me forever. Maybe it's easier to use a text box. And that would equal some number of centimeters per second. Grab yourself a calculator. 50 divided by 4.5 is equal to 11.1. So that bead was moving, on average, at 11.1. And we should be getting better at labeling at this point in the year. And the reason why we teachers bust your chops about the setup is so that we can, A, make sure you know what you're doing, but also your label is just sitting there for free for you now. You don't have to think at all. The label is exactly the setup for the problem, centimeters per second. That's your speed. You're used to measuring speed maybe in a car in miles per hour. That's a distance divided by a time, right? So this is a distance divided by a time, centimeters per second. Oh. If you can figure out how to do that a little faster with a text box. I don't know if copy and paste works, but whatever. That's the setup. My expectation is that all 6 of them look like that. Finally, as water leaves a stream where it's in a constricted channel and enters a large body of water, it's going to slow down. If it progressively slows down, it will drop off particles in a nice progressive pattern. Running water is an excellent tool in nature for sorting out particle sizes. If you've gone to the beaches here near Pulaski, Sandy Island Beach, Boaters Beach, I've never been to Brennan's, but any of those other ones, all the particles are the same size. You go to a sand beach, they're all sand. Where's the pebbles, cobbles, and boulders? They're somewhere else because the running water, the wave action, the longshore current of Lake Ontario does a great job of organizing particles by size. This is that premise. As water slows down, it's going to drop off the heaviest things first and then move progressively smaller and smaller and smaller. So you've got to go back to that earth science reference tables if you didn't memorize the 6 particle sizes, which I don't expect you to. Go back to the reference tables, go through those 6 particle sizes, and give me biggest to smallest on that thing. And you are good to go. Another lab down. All right. Great job. Again, this will all be over soon. We'll be back to hands-on labs. I know it'll be another year. You guys will be in a different class, but I really appreciate your patience and pushing through all this stuff. You're doing great. Okay. Keep it up. Sunnier days are soon ahead. We'll see you soon.